Hello, this is the next video on a playlist that I'm calling Yahtzee, where we look at all sorts of probabilities and of situations in Yahtzee. This is a follow-up video to where we're looking at how many ones we achieve in rolling. So the situation is we only have one category left. That's the number ones. We need the maximum number of ones, and then we score based on how many ones we roll, and that's it. And so I watched the previous video in the playlist, and here we're using R to calculate the exact probabilities. And again, you'll have to watch the previous video to understand what we did. But here's the first attempt at the calculation. And so we want to find the probability distribution for X equal to, X3 equals the number of ones in 3 rolls. It could be 0, 1, 2, up to 5. And the way we did it in the previous video, we let I be the number ones in the first roll, J be the number of ones in the second roll, K be the number of ones in the third roll. And we went through all these possibilities such that IJK equals the X value that we want. And this is the conditional probability statement from the previous video. But basically, we're accumulating all the cases that ij and k equal that X. And then boom, then at the end, this is the probability distribution. So about 1% of the time, a little over 1% of the time, you end up with a Yahtzee. And then about 35% of the time, you will get 3 or more. And that actually becomes a strategy in Yahtzee, because when you're calculating in the top portion of the Yahtzee scorecard, you count how many sixes, you get scores based upon how many sixes, how many fives, how many fours, threes, twos, ones. But if you average 3 of each of those numbers, then you get a bonus. And so that's why I highlighted this. Now there's another way to do this, is we create all possible cases. So on die 1, we could roll 0 through 5 ones. On die 2, we could roll 0 through 5 ones. Die 3, we could roll 0 through 5 ones. But that's too many cases, because the total of these numbers can't be more than 5. Because if it represents how many ones we rolled on each of those, how many ones we roll on the first one, we're going to set aside, and then we roll the remaining die, and then we set ones aside and we roll. So the sums can't be more than 5. So we have to keep all the cases such the sum is less than 5. And that's what we do here. So then we subset it. We keep only the cases that are 5. And let's look at the dimensions. It's 56 by 3. And this number is interesting because in the video before this, we said there were 56 terms that we have to add together to end up finding the probability distribution of the number of ones in 3 rolls. And so that's exactly what we just calculated here. So these are all 56 possibilities. So then we use apply, and we calculate the probability of observing that result in each row. So we go row by row, and we calculate the probability, which we said was the product of these, using the conditional probability statements. We said they were all binomials. So on the first case, we're rolling 5 die. On the second die, we're rolling, I don't know what I just did there. We're rolling 5 less than how many ones we roll in the first roll. And then on the third roll, we're setting aside the number of ones we observed on rolls 1 and 2, and then subtracting that from 5. So this is the probability that we observed each row, but we need to combine those based upon the row totals. So let's add that column. So we go row by row, adding the total number of ones, and then we take this probability and put it also in the data frame. And notice that if we table the row totals, this is what we get. But in the first video, this is precisely how many terms we said. If when x equals 5, we have to add 21 terms. When x equals 4, we have to add 15 terms. And so this exactly correlates with what we observed in the previous video. Then what we do is we aggregate, so we add up the probabilities by total when we're adding, and then this is what we get. So this is the exact probability distribution. So 1% of the time we get a Yahtzee, about 35% of the time we get 3 or more. And notice this is the same probability that we just calculated. As always, I add add the R code to the comments so you can copy and paste it and play with it. This is kind of a neat little simulation. First of all, we have to simulate rolling a die, so it's a discrete uniform. And we want to calculate how many ones we have at the end. And that's what pip is. Pip are the little dots on a die, and we want the side with 1 pip. Now you could change this to a 4, and then it calculates the number of 4s after 3 rolls. It's actually the same probability distribution. We want to run this experiment 500,000 times. So we're going to roll 3 rolls 500,000 times, counting the number of ones. Now this was, I think, pretty creative on my part. And I didn't do this at first. I sort of discovered it. I rolled 3 die, and then I looked at the observations. And I initially I was trying to grab the column names, or the names of the 3 rolls, to see if it was really tough. Then I discovered, right, so this random uniform could have some 1s or it could not have some 1s. But if I create a factor with 6 levels and then I tabled it, it would also table the numbers that I didn't observe in this random sample. So if I didn't observe any 1s, create a factor 6 levels, tabled it, it'd put a 0 under the 1s. Now if you didn't factor it, it just leaves out the numbers that you don't observe, so it becomes really tough. So I had to factor it, I tabled it, and I grabbed the first component, which is the number of 1s on these 5 rolls. Then on roll 2, I rep how many 1s we observed in roll 1, and then I roll the other remaining die, 5 minus how many I rolled, how many 1s I got on row 1, factor it, table it, and grab how many 1s. Now notice that these 1s, it's like being carried over, and I could add more 1s, but I grab how many 1s, and then we repeat it for roll 3, and then this is the total number of 1s that we observed. So boom, it sticks it in this vector, and then the component is by the loop, and I do it 500,000 times. I table the results. I create like a little proportions vector, and then that's what the right 2 columns are. And then this one was the theoretical calculations. And notice the theoretical calculations are like almost identical to the simulations, as they should be. Okay, well, that's all I have for this video. Again, I'll put the code in the comments if you want to copy and paste it, play with it, optimize it. You can optimize this one, but it's such a small space that you're not really going to optimize it much. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.